When we speak about the Internet protocol, we have also to speak about other protocols on the Internet layer of the TCP/IP protocol stack. There are many, and we will only cite some of them. That's also the reason we speak about the TCP/IP protocol suite. It's not only on the Internet layer that we have the IP protocol. On the Internet layer, of course, the IP protocol is the most important one. But on the IP layer, we have also the ICMP protocol, the OSPF protocol, the PGP protocol, the ARP protocol. We mentioned it with the translation of addresses. So for that reason, the ARP protocol is placed on the network access layer and a little bit on the Internet layer. And the same is with the reverse ARP protocol. So let's have first a look to the ICMP protocol. ICMP, the Internet Control Message Protocol. It is specified in the Internet Standards 792 and 1256 and has the following functions. The ICMP protocol is mainly needed for error diagnosis. It is needed to record timestamps, to detect expired timestamps, and to manage routing tables. So it provides a lot of helping functions that are needed to perform IP protocol and to perform it in the correct way. Also, flow control messages are sent by the ICMP protocol to avoid router overload. The determination of the permitted MTU, the maximum transfer unit. You remember this was important to know for the router to see in which way data packets have to be fragmented. The messages which are sent by the ICMP protocol, they are encapsulated in an IP datagram. So they are transported as a load in an IP protocol. To make visible that this is an ICMP message, in the protocol field of the IP header, we have the number 1. Here you see also an example why we need such a protocol field in the IP header. This is a data format of the ICMP messages. We have the IP header. In the IP header, like just mentioned, with the protocol number 1, indicated that this is an ICMP message. And the ICMP message, that's the payload of this IP datagram. And the ICMP message consists here of this type of a header type code checksum, very simple, and then the ICMP message. There are different ICMP message types. So for example, message type 0 is echo answer, target not reachable, throttable sending, change route. You see, I have not mentioned all messages that help to control the correct working of the Internet protocol. So this ICMP protocol gives and helps to send information for controlling the correct function of the Internet. Here an example. For example, host 1 wants to check whether another host in the Internet, perhaps placed in another network, is reachable. So this can be easily done by sending an ICMP message, and exactly the echo request message is sent. It's sent over the Internet inside an AP package, and this ICMP echo request reaches the desired host B. If host B is connected to the Internet, host B answers with another ICMP message with an ICMP echo response. This is transported, enclosed, encapsulated inside an IP package back to host A, and after receiving this ICMP message, host A knows, yes, host B is reachable. Otherwise, there is a failure message. Another example of an ICMP message here is to determine a router. This is a so-called router solicitation. It is requested by a message which are sent. It is a broadcast or multicast sent over the internet to the host, and then host answers with an entsprechend router advertisement explaining his address and giving the host A the possibility to interact with the router. To give another example of a protocol on the internet layer of the TCP/IP protocols, like let's have a look to the ARP protocol, the address resolution protocol, and the task of this ARP protocol is to convert a local IP address into the network address that's understood by the network. So for example, if we have a computer inside an Ethernet and we know it's a local IP address, then we want to know, the router wants to know the Ethernet address to forward the packets to this router. So what the ARP protocol is doing here from the internet, there is a package receiving at the router with an IP address 135.89.16.23. And the router has to find out what is the router recognize. Okay, that is the network, it's a local network, so the package has to be handed over to a host inside this network. So the router has to find out what is the Ethernet address, if it is an Ethernet, or what's the local network address, in this case the MAC address, and then the router analyzes the IP address and converts this into a MAC address, and this is done by means of the ARP, the address resolution protocol. How this address resolution is implemented. There are different possibilities. A very simple possibility is a table search. So the router has an internal address table for the translation, and he looks, if he gets an IP address and he sees it's a computer inside the network, he makes a table lookup and finds out what is the corresponding network address. But of course, such tables are only a meaningful approach if it's a small network. So there are other methods in place used by the ARP resolution protocol to transform an IP address into a network address. Another method is this, beside of table search, is this direct calculation. And here the administrator of a network tries to do the following. He tries to define a function which assigns an IP address the correct hardware address. This can be done if the hardware addresses are configurable, or if in the one side or in the other direction, if the administrator assigns IP addresses to hardware addresses, so that there is an easy mechanism to translate one into another. The prerequisite is that the hardware address can be determined in such a way that the calculation of this function f is very simple. This is the second method. And the third method is that the ARP protocol uses a message exchange. So that the router receiving a packet with an IP address sends a message into the network asking who of the hosts has this hardware address. So the ARP protocol, so the computer says with a correct hardware address, which realizes that the IP address, sends back to the router his hardware address. In this way, translation is possible. There are two possibilities. The one possibility is that this is a centralized approach. So here the ARP server responds with a hardware address, and we have the decentralized approach where the router broadcasts his request to all the computers, and the computers, the connected hosts, check by their own is this the own IP address, and then they send back as a response to the router their hardware address. So the ARP, all the work of this ARP protocol is done by exchanging messages. So there is here the following message format. There is the ARP request. An IP address is sent with a request for translation. Then there is an ARP answer. Here the IP address is sent back together with a hardware address. The problem that's quite inefficient for the following reason. Before the data transfer can take part, ARP request must be initiated. A solution here for this problem is that a cache is used. A cache is used to store the mapping of the IP address and the hardware address. It's a so-called ARP cache. So after sending a request and receiving an answer, the router stores in the cache memory this combination, and next time router gets a packet with an IP address, he first consults his ARP cache, the cache, before he sends a request to all the hosts inside a system. Let's conclude this, the last learning video of our week about internet working, with mentioning some problems around IP version 4. And we will do this as a motivation for the work we will do next week when we consider the IP protocol next generation. First, we have to state that the current IP version, and in most places this is IP version 4, it was a very successful, extremely successful approach. Why it was so successful? Yeah, when the IP version 4 protocol was designed, not even local area network technologies were involved. Meanwhile, we have computers, we have systems, routers, intermediate systems, which are magnitudes faster than in the time when the IP protocol was introduced. So the reason for this big success is that it is a well thought out IP basic design. It was possible to use this with new hardware. It was possible to use this with new network technologies. I mentioned IPv4 was developed before the dissemination of the LAN technologies. Also, the functions that are implemented in the IP version 4 protocol work even if the networks are magnitudes faster than the networks the IP protocol was designed for. And very astonishing, the IP protocol managed to cope with the enormous growth in the global heterogeneous internet. But we have problems today. We have problems not so much from the design, but from the problem that there are much more systems that want to be connected to the internet than IPv4 addresses are available. And you know, to connect a new device, a sensor, a smartphone, a tablet to the internet, it needs an address. So this enormous growth of the internet brought a situation that about 1 billion addresses that are possible to describe with 32 bits, strings of 32 bits, that they run out a couple of years ago. So this brought a situation that people, and this was recognized very early, have started to design a successor, a new IP protocol. It's IP protocol version 6, which overcomes some of the design errors of IPv4 and mainly provides enough addresses to connect also, to provide the possibility also in future to connect systems to the internet.